So today I'm going to be deriving the moment of inertia of a rod, which is a very important thing to be able to do because rod problems are going to come up a lot in your first physics class in either college or high school, and you might forget the moment of inertia of a rod. And so deriving it and learning where it comes from helps make it more memorable, and it saves you in a bind where you forget. So let's start by defining the definition of moment of inertia. So moment of inertia is typically the variable. It's represented by the variable capital I, and then it's the integral of the perpendicular distance, and then uh, an infinitesimal mass element. And so we actually don't use this definition very often. We typically use an equivalent definition, which is the same thing: perpendicular distance to the axis of rotation, and then a mass density, and then an infinitesimal volume element. So let me kind of draw kind of what's going on physically. So we have some rod. We're going to say this rod is like length L. Okay. So let's maybe move this down here actually. Oh, whoopsie daisies. Okay. So now there's also going to be some axis of rotation here as well, right? So let's write this is going to be W. Does that sound good? So it's rotating around this kind of vertical axis W. And then we got a length L rod here. So this is the rod. Now, this rod is going to have a total mass m, and it's going to have some mass density described by that total mass m over the length. So per distance, there is some amount of mass here. So what we can do now is we can do the moment of inertia equals x squared, because there's only one dimension, lambda dx. And we can perform this integral to find the moment of inertia. So let's do, and then we can also describe the bounds here too. So we can set our coordinate system. Our x will equal 0 at the axis of rotation, and then this will be x equals negative L over 2. This will be x equals L over 2. Okay, so let's put our bounds here for the integral. Okay, so now doing this, we get lambda x to the third over 3, and then negative L over 2, L over 2, and now this will come out to be lambda L to the third, 2L to the third over 3 times 8. And so now we remember that lambda is equal to m over L, so this will be m over L, L to the third over 12. And this will just come out to 1 over 12 m L squared. So hopefully that helps answer the question. And yeah, we just generically will sort of follow this approach for other kinds of moments of inertia we wish to derive, which I'll do in the future.